Good morning, everyone. So let's start. Today we will learn this thing: Euler's path, circuit, and Hamiltonian path and circuit. So before I start with Euler's path, I will be telling you a short story behind the Euler's path and circuit. So it is there in Rosen book. So I'll just read out for you all. The town of Königsberg, Prussia, which is now called as Kaliningrad and which is part of Russian Republic now. It was divided into four sections by the branches of Regel River. These four sections included the two regions on the banks of the Pregel. So from the diagram, you can visualize these regions that I'm talking about. So these four sections included the two regions on the banks of the Pregel and the region between the two branches of the Pregel. In the 18th century, seven bridges connected these regions. So you can see the bridges in the diagram in the figure 1. You can see the bridges and the regions. Okay. Now, the townspeople took long walks through town on Sundays, and they wondered whether it was possible to start at some location in the town, travel across all the bridges without crossing any bridge twice, and return to the starting point. Then a Swiss mathematician Leonard Euler solved this problem. So his solution published in 1736, and he maybe the first that was the first use of graph theory. Then he studied this problem using multigraph obtained when the four regions are represented by vertices and bridges by edges. So the regions are represented by vertices. So in figure 2, you can see the vertices are nothing but regions and the bridges are nothing but edges. Okay, so that multigraph he has got from the real-time application that townspeople were facing. Then the problem of traveling across every bridge without crossing any bridge more than once can be rephrased in terms of this model. So then he come across this Euler circuit, which we are studying, which we will study right now. So this Euler circuit, he says that we have to visit all the edges of a given graph without crossing any edge twice. It means you have to visit every edge only once. You're not supposed to count it twice, or you should not visit it twice, more than once. So, and accordingly, you have to find the path and circuit. Okay. And इसका उल्टा है Hamiltonian, जिसमें we consider vertices. We do not visit vertices twice. We visit vertices only once, and then we find Hamiltonian path and circuit. But then again, for these Hamiltonian and Euler paths and circuit, we have some conditions that we will keep in the mind, and it is not possible for all graphs to have Euler's path and circuit and Hamiltonian path and circuit. So if they satisfy particular condition, then only we try to find Euler path and circuit and also Hamiltonian path and circuit. So see, for Eulerian path, we have some condition. So the one written in red is our conditions. So all vertices with non-zero degree are connected. So a vertex with non-zero degree, it means except null graph. Null graph आपको यहाँ पे consider करना ही नहीं है. It is not possible at all. I mean उसमें कुछ calculate ही नहीं होगा. Because it will be having only one vertices or more than one vertices, but they won't be having any edges. So now here any graph where degree is not zero of any of the vertices. So we are talking about degrees more than one and more than one. So this is the first condition, and that graph should be connected. Second condition, if zero or two vertices have odd degree and all other vertices have even degree. It means there are no vertex which is having odd degree, or there are exactly two vertices which are having odd degrees and remaining vertices are having even degrees. Got this? These are two conditions. So first one is you need not to worry about, because they are talking about that it should be a graph, connected graph. Mostly we consider graph as a closed diagram. It means it is not open at any end. It is always having some circuits. So it is always a closed diagram. So that is for sure that you will be working on such type of diagrams only. But the second condition is very important for Eulerian part, that इधर जीरो वर्टाइसेस, मतलब कोई भी वर्टेक्स ऐसा नहीं है जिसका और डिग्री है, मतलब ऑल वर्टाइसेस आर हैविंग इवन डिग्री. और दूसरी कंडीशन ये है that exactly two vertices are having odd degrees. Then only you find Eulerian path for a given graph. So you have to check the second condition. If it is not satisfied by any graph, then we say that Eulerian path is not possible for given graph. So see, can someone tell me whether Eulerian path is possible for this graph or not? Can you check the condition? Yes, is it possible? Am I audible?
Yes, ma'am.
So is it possible for this diagram to have Euler path? It is written over there. So see, everybody will calculate this thing. So let's see, the degree of 1 is 2, degree of 2 is 2, degree of vertex 0 is 3, degree of vertex 3 is 2, and degree of vertex 4 is 1. So there are two vertices 0 and 4 which are having odd degrees, and all other vertices, that is 1, 2 and 3, are having even degrees. Okay, so this is, in this graph we can find Euler path. Okay, so see, the Euler path is already given over here. Okay, for given graph there are multiple paths, so you can have any, you can find out any path for this given graph, provided you are traveling edges only once. Okay, that is also a condition. So this is one of the graph 430120. See, 430120. Okay, we are not going back to 4 because we are talking about path. Path is having different starting and end points. Okay, we are not talking about cycle here, cycle or circle. Okay, another path can be. Can someone tell me? Is there any other path which will include all ages and only once, and we will not have same start point and end point?
0 to 1 0 3 4.
1
0
2 0 3 4.
1 2 0 3 4 नहीं, you are not counting this age in that case. 1 2 0 3 4 में you are excluding this age. We want to cover all ages once.
0 to 1 0 3 4.
0 to 1 0
0 3 4.
4. Correct. Anything else? 0 1 2 0 3 4. Okay, that is also Eulerian path. Okay, so are we clear what is Eulerian path? Shall I
Yes.
go ahead? Yeah. So Eulerian cycle or circuit, here also the first condition is all vertices with non-zero degree are connected. Okay, so it should be proper graph, and then second condition is all vertices having even degree. So Eulerian conditions for Eulerian circuit is very simple and straightforward. So you just look for this thing, um, whether all vertices are having even degree or not. Also, for Eulerian path, can we consider triangle as an example where we can find Eulerian path? Is it possible for a triangle to have Eulerian path?
Yes, ma'am.
Yes,
Yes.
because zero vertices will be having odd degrees and all other vertices will be having even degrees. So cycle is also having Eulerian circuit, so that is also possible. Sorry, triangle is also having Eulerian circuit, so that is also possible for triangle. So see, all vertices are having even degrees now. We have got this line over here connecting 0 and 4. So now 0 and 4 are having even degrees. So all vertices are having even degrees. So you can start from any point and you will get the Eulerian path. But then keep in the mind that you are not skipping any edge. Okay. So you want to cover all edges only once. That is the main focus of Eulerian path and circuit. So we start from 0, 1, 2, 0, 4, 3, and 0. Okay. So that is one Eulerian circuit. Then the one given over here is 2, 1, 0, 3, 4, 0, 2. Okay. So this is Eulerian cycle or circuit. Okay. Is there any doubt?
No, ma'am.
So these are some applications of Eulerian circuit and path. Where in telecommunication you will find that you don't want to cross any connection or something like that. So there also you can have you can use Eulerian path or circuits to connect different houses for, and then parallel programming. Parallel programming is the one where CPU, there are n number of cores, and what we say, CPUs, not exactly CPUs, but there are different cores where we run everything, we execute every program. So when you have multiple cores in your CPU, suppose I have 5 cores in my CPU, so I want to run a particular program. This parallel programming is another concept. So where I want to run my piece of program parallelly on each and every core. So what will happen? I am executing part 1 on core 1, part 2 on core 2, and simultaneously 3, 4, 5 on core 3, 2, 4, and 5. So they will execute exactly at the same time. I mean, parallelly they will get executed. That is parallel programming. It has, I mean, CUDA is the platform where you can run. Plus, you need some hardware in your machine to run that type of programming programs. So for that also, you can have this, Euler circuit and paths, whether which core will run which code, and accordingly you can draw a graph and you can you know uh, implement it in your programming, and it will get executed. So you just, there are so many applications over here, but these are two which I pick, which are related to our field. So yes, the next one is Hamiltonian path and circuit. So in Hamiltonian path, we visit all vertices exactly once. So like unlike Eulerian circuit or path, you are not supposed to repeat any vertex here. Yes, you may repeat edges, but you are not supposed to repeat any vertex. So there is no such condition in Hamiltonian path. So just you have to keep in the mind that you are not repeating any vertex. So see in this diagram, if I start from 4, 3, 0, 2 and 1, that is my Hamiltonian path. Okay, I am not worried about ages. If this age is skipped, then also it is okay for me, but I have to, what is my motto? I am not going to repeat any vertex. So 4, 3, 0, 2 and 1 is one path, 1, 2, 0, 3, 4 is another path. Okay, so likewise you can have different parts, Hamiltonian parts. Uh, are we clear?
Yes, ma'am.
Then Hamiltonian circuit, it is also the same thing, where you have to visit the vertex exactly once, but now it is the circuit, so you have to end at the same point. Okay, so if you take triangle ABC, then you start from A, then visit B, then C, and go back to A. This way you can have Hamiltonian circuit. Okay, so that is the example of, this is also an example of Hamiltonian circuit. You start from this point and you are going from this is the path they have drawn. You started from here, you went here, here, and you reached here again. Likewise, so you have covered all vertices of this graph, and you have reached the same point where you started. Okay, so this is Hamiltonian circuit. Then there is Euler's formula to find out how many regions are there in your what we say graph. So the one we studied previously was also examples, sorry, formulas for spatial graphs where some conditions were mentioned. But then if you are having a planar graph, you can always use this formula as well. So which is R is equal to E minus V plus 2. R is number of regions, E is number of edges, and V is number of vertices. So even you can use this formula to calculate number of regions, or if number of regions are given, you can calculate number of edges provided number of vertices are given. Okay, so small simple formula. Then the isomorphism of graphs. So in this, as I have told you that in groups we have seen isomorphism, but then that was the same concept is applicable here also. We are checking for one-to-one correspondence of two graphs, but in terms of vertices and degree of those vertices. Okay, so I'll just read out this thing. In graph theory, an isomorphism of graphs G and H is a bijection between the vertex set of G and H. So we are looking for bijective function here. So we are looking for one-to-one correspondence and on-to correspondence also. So that adjacent U and V are adjacent vertices in G, and if and only if f of U and f of V are adjacent in H. I'll be explaining this. Okay. See, these are some steps which will tell you whether two graphs are isomorphic or not. So see, first you have to check whether those two graphs are having same number of vertices or not. If they are not having same number of vertices, just forget about it and declare that they are not isomorphic. Now, if they are having same number of vertices, then go on checking the vertices of having same degrees, number of vertices having same degrees. Okay, so you have to check whether graph 1 is having two vertices of degree 3. So you have to check whether in graph 2 is having two vertices of degree 3 or not. Okay, so if they are same, then you need not to worry about it. You just proceed further to count whether other vertices of having same degrees are same in number or not. Okay, then same degrees for corresponding vertices. Okay, I'll be telling you this. Same number of connected components, same number of loops. Okay, the first two conditions are done. You need not to calculate number of edges. Okay, because if number of vertices are same and if number of vertices having same degrees are also same, then you can directly say that two graphs are isomorphic. Okay, see, look at this graph. So here in this graph I have four vertices, and also in this graph I have four vertices. Okay, so now our next job is we have to count vertices of having same degrees, number of vertices having same degrees. So here 2 is having degree 2, all vertices are having degree 2, so 4 vertices are there of degree 2. So in this graph also we have to check whether this graph is having 4 vertices of degree 2 or not. Okay, so see, all vertices are having degree 2. So we can say that they are isomorphic with each other. Okay, girls, just give me 2 seconds. I'll be back in 2 minutes. Yes. Am I audible?
Yes, ma'am.
Yes, ma'am.
So these two graphs we will call them isomorphic. Okay. So if you look at this graph, these two graphs, so here all vertices are having same degree. So what we can do is we can have one-to-one correspondence between any vertices of this graph with any vertices of this graph. Okay. So it means one is mapped with 4, 3 can be mapped with 3, 2 can be mapped with 1, 4 can be mapped with 2, something like that. Okay. So you can have mapping in any way for this graph because all vertices are having same degree. Okay. So you can map any vertex with any other vertex of this graph because of that reason. Okay. Now can someone tell me which of these graphs are isomorphic? Suppose first one is G1, second is G2, and third is G3. So tell me which of these are isomorphic.
All of them.
Sorry,
All of them.
all of them are isomorphic with each other.
Yes, ma'am.
Yes, ma'am.
Okay. Now there is Dijistra's algorithm, but then we will learn it at the end. So let's complete these remaining concepts. So what is graph coloring and chromatic numbers? So graph coloring is the concept where you color the vertices, and the only condition is no two adjacent vertices share the same color. See the one written in the red color. So that is the only condition in graph coloring. So here the number of colors you require to color a given graph is called as chromatic number. So for a triangle, if I need three colors to color the vertices of that triangle, and the condition is adjacent vertices should not have same color, then the chromatic number for that graph becomes 3. Am I right? Green, blue, and red. Because every vertex is adjacent to every other vertex of the triangle. Okay, so let's see how it can be done. Okay. I'll just open whiteboard here. I don't have example on graph coloring. Can someone tell me how many colors are required to color this graph, vertices of this graph?
Four.
No,
Two.
correct. See, if I take green here, I cannot take green here and here. Okay, so I'll take blue here. So if I take blue here, I can't take blue here and not here also. But then I can use green here because this vertex is not adjacent to this one. I hope you understand adjacent vertices. So they are not connected. It means they are not adjacent vertices. So I can use green here. Okay. And sorry, it is not 2, it is 3. So green and blue is done. Can I take green here again? No, because this is also green and this is also green. So I have to choose another vertex, another color which is red. So this is how I'll color my vertices. Okay, so 3 colors are required, and you are supposed to find the number of colors, minimum number of colors. Okay, ऐसे नहीं है कि 4 vertices तो you have taken 4 different colors. It is not like that. That is not the chromatic number. So minimum colors required to color this graph is chromatic number. So we are not talking about maximum number of colors required. We want कम से कम में कितना होगा coloring, that number we want. Okay, so this is graph coloring. Also I will give you one more example. Okay, there is this age, just forget about this age and just see whether the eraser is there. Yes, tell me the chromatic number of this graph.
Three.
3 again, 3.
Three.
Let's see. Green is there, and I can't take green here, so I have taken red over here. I can't take red here. Can I take green here?
No.
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 So I have to
No.
choose another color, that is blue. So I can't take blue here. Can I take red here? Can I take green
No.
here?
No, ma'am.
I can take green here. Okay. Can I take blue here?
Yes.
Yes.
Yes. So how many colors are there? The chromatic number is, okay. Now comes the traveling salesman problem. So here we have a traveling salesman. The salesman always travel from one place to another place, and he always look for the minimum path. Minimum path in the sense that the places connecting each other having minimum distances, or the minimum distances in which he can cover more places. Okay, so this problem is related to him only. So we have this salesman and set of cities. Okay, so salesman and set of cities can be represented by a graph. Set of cities connected with each other can be represented by a graph. So the salesman has to visit each one of the cities starting from one certain uh, place and returning to the same city. Starting from one city and returning to the same city. So he's coming back to his own city. So the challenge is we want to minimize his total length of the trip. So in a given triangle, if there are A, B, and C cities, then he want to start from A, B, and he want to start from A, travel B, C, and come back to A. So in a triangle, it is possible that there is only one way that he can travel from A and reach B and C. Okay, but then what about graphs which are having more than 3 vertices? So suppose this is our graph, okay, or I'll draw it here. Suppose this is one city, 2, 1, 2, then 3, then this is 4 and 5. Okay, so this is his starting point. Okay, he's starting from this one. Suppose he's starting from this one, and you may start from any point. So these 1, 2, 3, 4, 5 are cities. Okay, and the edges will be the paths connecting those cities. Okay, now he started from 1, he reached to 2, then he went to 4, then he went to 5, then he went to 3, and then he came back to 1 again. Okay, Now we don't know the length of or weight of these edges. Okay, do you understand weight of these edges? That 1 to 2 is having weight 5, or 2 to 4 is having weight 6, something like that. So right now we don't know the weight of these edges. We are just looking for the general solution for this graph. So this is one way he can travel these 4 cities, and there is another way also that he can start from city 3, then go to 4, then 5, then 2, and then go to 1. Okay, this is another solution. There is another solution that he started from 1, he went to 5, then 4, then 3, then 2, and came back to 1. Okay, now we are telling him so many paths right now, but then we don't know which one is minimal path. So you should have the weighted graph for this problem, and you keep on considering the edges which are having minimum weight. Okay, so let's see, this is having 5, 6, then 7, this is 2, 3, 4, and 9, and this is having 7 again, and this, okay, we have already considered this age is having suppose 6. Okay, so now when you start from 1, you always choose the 1 to 2 is 5 units and 1 to 5 is 3 units. So which one you will pick? 3 we will pick. Okay, then you reach 5, then here from here you select the minimum path. So 5 to 4 is 4 units, 5 to 3 is 7 units, 5 to 2 is 2 units. So you'll go to 2, second city. Then from 2 you'll select minimum distance. So it is 6 and 7. 2 is already taken, so we will not consider it again. So there are only 2 choices from 2, either 6 or 7. So we'll choose 6. So he went here. Then after that, from 3, how many choices are there? 7 and 9. So he will choose 7. Then from 5 again he has how many choices? Only one choice is left because this and this is already covered. So he will go to 4. Now from 4, how many choices he has? He can't take this thing. Okay, we should connect 4 to 1 also, because from there he is going to 1. So from 4, he suppose is having 3 distance. So now from 4, there are 2 choices, 7, sorry, going towards 1 is only 1. So he'll choose 3 and he'll come back to his city. So this is the way he chooses his minimal distances, and he travel from one city to another city. Okay, got this? Right now here in discrete mathematics, we are just learning the theory of traveling salesman problem, but solving the problems is not included in this in our syllabus. But yes, they are kind of similar to Dijkstra's algorithm, which also solves a given problem to find the shortest distance from one place to another place. And but in Dijkstra's we have different starting point, different ending point. So that is the difference between traveling salesman and Dijkstra's algorithm. Okay, is there any doubt in this one? Because right now it is 9:45. 15 minutes में Dijkstra's algorithm नहीं होगा. Okay, so can we stop here now? I mean, if you don't have any questions. Do you have any questions?
No, ma'am.
Snehal, you asked, what was your question?
Ma'am, actually, in the starting, during the Euler's thing,
Huh? Circuit?
Ma'am, during the Euler's path, like we had started from 430120, right? So the other path you said was 021034. So I was confused whether it's the same thing, reverse and back.
Okay, okay. But are you clear now?
Yes, ma'am.
Okay. Okay, so we'll stop here now, and in the next lecture, we will learn Dijistra's algorithm, which is the last topic of this unit. And then we'll start with, so probably in this week, we will finish with the syllabus of discrete mathematics, because trees is very simple unit and has a very simple concept also. So once you know what is graph, you will understand what are trees. They're part of graphs only. And then short algorithms are there: Prim's algorithm and Kruskal's algorithm, and also uh, traversals of tree, how we traverse a particular tree. Even we can traverse mean how you go through your graph or go through your tree. So that is traveling. Okay, so I'll share your attendance form here now. There is one Google Sheet I have shared with you all. So I request you all to write down. It was for only Unit 3, but I'll request you all to write down all your doubts over there, starting from Unit 1 to Unit 5, sorry. And after we are done with Unit 6, we will discuss all doubts in our classes, because we have almost 2 weeks in our hand, which are extra, so we can discuss doubts over there. So I want you to take advantage of that. So I have shared the attendance form. Mark your attendance and you may leave. If you have any doubts, please ask.